Hi everyone, this is the first video in Unit 2, the derivative and the tangent line problem. You should have already watched the shorter video on the tangent line problem and collected some notes and special terms that we're going to use again in this video. The shorter video was the concept video, and this one will be more of the practical and some examples for your problem sets. Write down the objectives that are listed here, and here we go. So on this page, it's just full of notation. This part up here you recognize from the previous. It's the definition of a derivative using the limit notation with delta x instead of h. Here are some other notations that are used to denote the derivative: f prime, y prime, d of the function dx. I've never seen this one, but I wrote it there anyway, and then dy dx. And then this is all of the notation kind of all mixed together. So the derivative is equal to the limit definition, which is written a little bit differently, change in y over change in x, the limit definition, and then y prime. So here's our first example. We are going to find the slope of the tangent line to the graph at a point. So here's my graph. This is the equation of a line at the point 3, -4. To find the slope of the tangent line, we need the derivative. So we're going to use the limit definition of a derivative. It's the only rule we know so far. You recognize the function notation. We know what f of x is. F of x is 5 minus x. We need to find f of x plus h. So I'm going to write that over here. F of x plus h is equal to 5 minus, and then instead of the x, I'm going to replace it with what's inside the parentheses, x plus h. So simplifying, I would have 5 minus x minus h, right, because you're going to distribute the negative. So let's fill in the parts. So I have the limit as h approaches 0 of f of x plus h, which is 5 minus x minus h, minus the function f of x, which is 5 minus x, all over h. Now, once again, you're subtracting a function, so that means that you have a distributive property happening here. And so you're going to end up with the limit as h approaches 0 of 5 minus x minus h minus 5 plus x over h. Now, when you're at this point, you're going to be simplifying the numerator. And a rule of thumb here, and this will always, this is the word always, happen, if one of the terms does not have an h in it, no h, no h, there's an h, no h, no h, anything without an h is going to cancel. And if it doesn't, you did something wrong. So 5 minus 5, negative x plus x, right? So you're going to be you're going to end up with the limit as h approaches 0 of negative h over h, which that just reduces to -1. That's going to be the slope of the tangent at the point 3, -4. The second example that we're going to do is the same kind of problem, but it's asked a little differently. So instead of finding the slope of the tangent line, we are going to find the derivative using the limit process. Once again, the definition of a derivative using the limit definition is written over here to the right. We're going to use it, and we're going to do the same thing. Now, what makes this problem different is that this isn't linear anymore. So this is squared. So I'll show you. So we do f of x plus h, and that's 1 minus x plus h quantity squared. Now, I'll probably show you in class a pretty simple way to multiply this out. I'll do it rather quickly here, but really the pattern of multiplying out a binomial that's squared is to square the first term, square the last term, and then the middle term is x times h doubled. And that's true every single time, like every single time. So anytime you have to square x plus h, you're going to end up with x squared plus 2xh plus h squared. So don't do the rookie mistake of saying it's x squared plus h squared. Like, No, leave that behind. All right, so once again, the negative gets distributive, so 1 minus x squared minus 2xh minus h squared. So I've just distributed that negative all the way across. All right, so the limit as h approaches 0 of, and I've already got it figured out, so 1 minus x squared minus 2xh minus h squared minus the function. I'm going to go ahead and distribute, so negative 1 plus x squared, which I know it has to be that way anyway. Do you remember why? So the 1 doesn't have an h. 1 minus 1 is 0. X squared doesn't have an h. 2h and h squared, those all have h's. Okay? So on the top, I'm going to factor out an h from what is left, and I end up with negative 2x minus h over h. The h's cancel. They have to, or because you can't divide by 0. And then remember how we evaluate a limit. The easiest way is substitution. So I'm going to substitute a 0 for the h in the problem, and I end up with negative 2x. So the slope of the tangent line to that curve is negative 2x. And that's all the tangent lines, all of them. Because the domain for a quadratic is all reals. So depending on where x is, it's going to have a different slope. So that one's real interesting. So we're going to use this one in the next problem. So our third and final example has us finding the equation of a tangent line to the graph at a given point. So a couple of things that we need to know here is, what do we need for an equation? What is a tangent line to a graph at a point? And so they've given us a function. You'll recognize this from the previous example. When we found the derivative, or we found the slope of the tangent line, we found it to be negative 2x, right? That was at the end of the last example. So we don't need to redo that work, but to find the derivative with the limit process, we would have completed that before. So in order to write the equation of a tangent line, we're going to use something called point-slope form. Point-slope form of a line. And you get point-slope form of a line from the slope formula, which, you know, the slope is the change in y over the change in x. And so then if you multiply the denominator to the other side, I tend to write the y's first, you end up with this form. And that's the point-slope form of a line. This is really important because we're going to talk about this equation of a line tangent to a graph at a given point throughout the rest of the course, off and on, clear through, and it will be on your AP exam for Calculus AB. So you need to get this down. The good thing is it's the easiest form of a line to use, because all you really need is, guess what? A point and a slope. Well, we've almost got the slope. These are all the slopes of all the lines tangent to the graph of 1 minus x squared, but we just want the one that's at this point. So we're going to plug in a 2 for the x, and the slope at 2 is going to be negative 4. So now we have a point, and now we have a slope, and so all we have to do is write it. So y minus, the y term is a negative 4, so plus 4, equals the slope x minus 2. X goes with x, you know, x and y. X goes with x, y goes with y, and this is the slope. And you're done. That's it. Stop. Full stop. So let's do some summary exercises. Let's talk about this. This is the difference quotient, right here, is the slope of the secant line. 2 points on the line, right? No limit. If you add the limit to the difference quotient, the limit as h approaches 0 of the difference quotient is the slope of the tangent line. And you need to write these down in your notes. Therefore, the slope of the tangent line is said to be the limit of the slope of the secant line. So here is the last summary page. And these are really important concepts that we're going to continue to go over. The derivative is the slope of a tangent line to a function at any point on that function. And that's not the whole story, but that's a start. The instantaneous rate of change at a point is just another name for the derivative. It's the instantaneous rate of change. It is the slope of a tangent line. There are all these things. If a function is differentiable at a point where x is equal to some value c, like 1, 2, 3, 4, 5, c, then f is continuous. So being differentiable implies being continuous. Well, what is continuous? Continuous, it's probably easier to define discontinuous, not continuous, a hole, a jump, or an asymptote on a graph. However, if f is continuous, no holes, jumps, or asymptotes at this point x equals c, then the function may or may not be differentiable at that point. In other words, there may or may not be a tangent line at that point. There may or may not be instantaneous rate of change at that point. There might be a sharp corner. So continuity does not imply differentiability. So be sure you get all of these words down in your notes so that you can refer to them later on. Make sure you watch the other video with the concept of the tangent line problem, and then I will see you in class.